The next algorithm we are going to learn is called bubble sort, because what happens in bubble sort is that the biggest item is going to continuously bubble to this top. The way it works is that each iteration that we do, we are going to compare adjacent pairs of items. And if they're in order, we do nothing, like this case. However, let's go ahead and swap them. If we find an adjacent pair, like this over here, bad one. If we find an adjacent pair like this, where it's out of order, we have to swap them. Okay, so we just care about adjacent pairs in this scenario. All right, so let's go ahead and sort these. And what you're going to see is that the biggest item will bubble to the top of each iteration. So this pair is in order. What about this pair? That's in order. And this pair is in order. What about this pair? They're out of order, so we swap. This pair, out of order, so swap them. What about this pair? They're out of order, right? The smaller thing should be on the left. The bigger thing should be on the right, so we swap them. Right? And boom. And notice that the biggest item, just kind of this big one over here, it just bubbled its way to the top. Okay? So, for sake of optimization, we can kind of just cut it off right here and only be concerned about this subsection of the array now. Okay? Don't have to worry about him. Right? So these guys are in order. These guys are also in order. These are in order. These aren't. Swap them. And then these aren't in order, so we swap them. Now we notice that the biggest one of this subsection has bubbled to the top now, so we can just leave it to the side. All right? And now actually, if you're kind of looking, it's already sorted, but with the way we've described this algorithm, we don't know that yet. But I'll go into how we deal with that later. But okay, we look at this pair, we look at this pair, we look at this pair, look at this pair, biggest item's bubbled to the top, so we're good. So when we look at this pair, this pair, this pair, and so we're good. And so on and so forth until the whole thing is sorted. All right. So if we do this, so there were n items. If we do if we do n minus 1 iterations, this is going to be guaranteed to work, right? Because we'll move the top n minus 1 items, so the biggest n minus 1 items over to the top of the list, and the last item is going to be left by itself, and that's fine. Right, that last item is going to be the smallest. Right, so now let's go ahead and optimize this just a bit further. The way the more optimal algorithm says, though, is that we kind of program when we stop as an indeterminate loop. Don't do it n minus 1 times. We will do an iteration. We will keep doing iterations until we get to an iteration where we didn't have anything to swap. So if this doesn't happen in this example, then I'll artificially generate one for our next example. Okay, so here we go. Let's go through. These pairs out of order, so swap. This pair's out of order, so swap them. This pair's out of order. Sorry, no, in order. This is out of order. This is out of order. This is out of order. Whoop! Boom. What about this one? So now this is fine. So we swapped at least one item last iteration, so we aren't done yet. So this is fine. This is fine. This is fine. This isn't fine. This isn't fine. Yep, this looks like we'll have to go all the way through this one. So we had swapped something last iteration, so we have to keep going. This is fine. This is fine. This isn't fine. And this isn't fine. So we swapped some stuff last iteration, so we have to keep going. This isn't fine. Sorry, this is fine. This isn't. And this isn't. Keep going. So that's fine. That isn't. And now we're last pair. Swap. One item left. No swaps to be done. And so we're done. Alright. So how much time does that take? It takes O of n squared comparisons in the worst case scenario. And as we'll see, it also takes O of m squared comparisons in the worst, O of n squared comparisons and O of n squared exchanges in the worst case scenario, as we'll see in a bit. But let's go ahead and take a look at a case where bubble sort is actually pretty useful. And that's if basically only a part of the list is unsorted. So let's go ahead and take these three over here, these three items over here, and we'll just swap them around, right? So we've got But we'll do this, where we've got basically a subsection of the array that's been inverted, right? So here, this isn't fine, so we swap. This isn't fine, so we swap. This isn't good, so we swap. And then we're good here, good here, good here. Don't bother checking this last item. Okay, biggest item's down at the top. Here, this needs to be swapped. Here, this needs to be swapped. Okay, this is fine, this is fine, this is fine, so we're good here. We had swaps last time, so we know we have to keep going. Swap here, here, no swap. These are fine, these are fine. So we're done here. Now notice that it's already sorted, but we did a swap last time, so we have to go through again. That's fine, and that's fine. And we got to the end without having to do any swaps, so we know we can stop right now. We know that it's sorted if we got through an iteration without swapping, so we're good here. So that means, by the way, that if I pass in a sorted list like this, right, this pair, this pair, this pair, this pair, this pair, this pair, they're all in order. So I went through in a single iteration, it's sorted. There were no swaps, so we're done. Right? Best case scenario is O of n time, right, with no exchanges. That's pretty good. Okay? On the other hand, worst case scenario, as for almost everything, is passing it in completely reversed. Right? That wasn't as elegant as it could have been. Maybe just need bigger hands for that. Worst case scenario, right, what happens? It's completely reversed, so this is bigger than this, so swap, 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 right? Oh, this is bigger than everything else, so swap, 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 and then swap, and then finally we're done. That took O of n squared time and O of n squared comparisons. So, O of n squared exchanges and O of n squared comparisons. So bubble sort, worst case scenarios, worst case then is worse than selection sort. However, it's got a pretty good best case. So we're going to move on next to kind of the best of these O of n squared algorithms, and it's actually so good that we do actually use it in practice, and that will be insertion sort.